Okay guys, so that brings us to 2.7. This is what the topic we discussed today, which is limits. It starts on page 30 of the best book. So, I showed you the formal definition in class, I projected it up, and again that's on page 130, so you can refer back to the little gray box there that gives you a formal definition of the limit. And I kind of modified the wording, and I don't know if this is going to be helpful or hurtful, I hope it's helpful. But a function f has a limit, a number. A limit, which they're calling L in the book, is just a number, at some point where x is equal to a, denoted like so, okay? The limit of whatever this function is equal to 5, 6, negative 12, whatever. If we can make function output values, that's the y values, the height of the function, really close, but not equal to that point in question, to that x equals to a. Okay? Algebraically speaking, you're going to be looking at rational functions or polynomial functions. Now, I'm going to jump down here. Polynomial functions, they're never a problem. They're nice, smooth, continuous functions. There are no holes or breaks or jumps. And so, you can just plug in whatever number x is going to, and you're going to get a number. It's that easy. With a rational function, you can still plug the number in. You can substitute whatever x is approaching, but there might be a problem. So generally with the rational functions, we're going to factor those. Okay, so just keep that in mind. So let me show you a polynomial function real quick first. So this is just some random polynomial that I made up a minute ago. And what I'm asking you to do is find the limit, or the height of the function, when x approaches 2. So remember, we're going to get really close to the number 2, where x is equal to 2, from the left and the right, but we're not actually going to go onto the point. So again, it's sort of like standing at the edge of a round pool. You're really close to going into the hole or into the pool, but you don't quite go that far. You just keep standing on the edge. Okay, so I have this function, it's a polynomial, and if I plug the 2 in, then I get 13. So the limit as x approaches 2 for this particular function has a height of 13. Now let's look at that graphically for a second. So, you put your function into y1, and you hit the graph key, and my window may not be good. Okay, so I'm just going to jump up on the x-axis. We'll make y-axis rather 25, let's say. And the reason being is because if x is 0, then the height is already 9. So anyway, we have this nice smooth quadratic polynomial. And the idea is I want to evaluate this, the limit, as x approaches 2. Well, let me use a pencil so I don't mess up my screen. When x is 2, what's the height of this function? Well, I can count these little, units here. Hopefully it's 13, but rather than that, I can do second table key, and I can go look, hey, look at that, where x is equal to 2, y is equal to 13. So the height of the function is 13. Now, the tangent line to the function at x equals to 2 is definitely not 13. In fact, it's going to be quite a different number. It's going to be 8 times 2 is 16 minus 6, it's going to be 10. Okay, so the derivative, the limit as h approaches 0 of f of 2 plus, let me write that, okay? The derivative f prime of 2 is equal to the limit as h approaches 0 of f of 2 plus h minus f of 2 all over h, right? We do this thing the long way. And I'm going to do it quickly using the power rule because I don't want to do the long way right now. I'm trying to make a point here. So it's 8x minus 6. So if I evaluate that derivative when x is 2, I get 8 times 2 minus 6, or 10. So the slope of the tangent line at the point on this function when x is equal to 2 is 10. But the height of the function, the limit, if I take my, let me make it bigger, if I take my limit and my fingers and I go from the left and the right to where x is equal to 2, and I get really close to the edge of that point, to the edge of the round swimming pool, but I don't jump in, then what I'm going to find is that the output value of the function, or the height of the function, is 13. Okay? Derivative, rate of change of a function at a point, limit, how close can we get from the left and the right, and maybe get the same output value. Okay? So let's go to the rational function. Here's a rational function, and I can just plug the 3 in, but right away I can see if I plug a 3 in, I've got 0 in the denominator, and that's very bad. So what you want to show a grader is you're going to rewrite this, but you're going to factor it. And you're going to factor it because we've got a removable discontinuity here, so when we cancel these two factors, we're left with the limit of x plus 2. So we've redefined the function, we've removed that little hole in the graph, and when I plug the 3 in, I get 3 plus 2, or 5. So let's look at that graph real quick. You see, I prepared, I already put them in my calculator. Oh, look at that. Now, you might say, well, why is it a straight line when, you know, the numerator's x squared? Well, because it's really a linear function. But what do you notice here? You notice that at x equals to 3, there's a hole in the graph. Okay? So there's a problem there. So I can get really, really close to the edge of that hole from the right, or I can get really, really close to the edge of the hole from the left. But if I go across to look at the output value, it should be 5. Now, in case I'm not sure, I'm going to look at my table, because that clarifies it. And as you can see, I've got an error at x is equal to 3. If I look from the left, I'm approaching 4, and if I look from the right, I'm approaching 6. So what you can do is 4 plus 6 divided by 2 is 5, right? The other thing you could do, a little trick, and you'll do this on occasion because you'll have to, is change your table. You notice my table's going 0, 1, 2, positive and negative. If you do second table set, my table's starting at -5, but that doesn't matter. I'm going to start at 0. The change in the table is what's important. So I might do, 0.25. And do second graph again. And what that's going to do is it's going to give me different increments. So again, if I go to where x is equal to 3, what you notice is from the left, the numbers are approaching 4.75, so it's getting closer to 5. And from the right, let me just scroll down a little bit more. It started out at, 6 point something, and then they're getting smaller and smaller and smaller and approaching 5 again. So if I refine this to maybe, 0.01, let's just try it. So table 0.0, let's do 0.05 and look at this table again. Now what that does is make my increments even smaller. And what you'll notice is as you keep changing that, so I got to get to 3, there's my error. Now you notice from, let me scroll up a little bit more, from the left we're really getting much closer to 5, and from the right we're getting closer to 5. Okay, if you scroll down here it's going to be 6, 7, whatever, but it's going to take you forever to get there. So you can look at it in the table and see it really clear, because remember, sometimes when you look at a graph, you're not always going to see the hole in the graph. Okay? And by the way, if I change that function, if I modify it by removing the discontinuity, so what did it become? X plus 2, right? What you're going to notice is it's the same exact function, it's linear, but now the hole is gone. We've removed the hole, the discontinuity, in the graph. And so, I'm still going to have a height of 5. Now the slope of the tangent line there at 3, that's going to be a completely different number. Alright, I'm not asking for the derivative at the point where x equals to 3. Even though this notation looks very similar to the derivative, I'm asking what is the height of the function when x is equal to 5. And another thing you can do is you can press your trace key and hit 3. So at x equals 3 and hit enter, and it'll give you the height of the function there too. Now, you might find that easier than scrolling through a table. Okay? What else was in this section? Oh, yes. The other thing that's really important that I pointed out in class is that in order for a limit to exist, the limit on the left must be equal to the limit from the right. So, graphically speaking, or from a table, there's 3, right? If I'm coming from the left, and the height's 5, if I come in from the right, the height is 5, so since the limit from the left is equal to the limit on the right, then I can say the limit as x approaches 3 is 5. If that doesn't happen, then the graph is probably broken. There's a break in the graph. The other thing that I did not mention in class, so this is important, is that the limit as x approaches any number of a number is the number itself. So an example, the limit as x approaches -2 of 5 is 5. Okay? I don't know. The limit as x approaches 1 of 17 is 17. Okay? And there's one other special thing too. If I have something like the limit as x approaches 3 of x, well, my function is x. Well, the answer is going to be 3. Okay, so you see how these two match? So let me put that in there. I didn't prepare enough. Let's graph y equals to x. And it makes sense, right? Because when x is 3, y is 3. Let's try it. Trace it, right? When x is 3, y is 3. If I have the limit, as x approaches -1 of x, well, the answer is -1. Why? If I look at the graph, or I do a trace -1, whatever x is, that's what y is. So the height's going to be the same as what it's trying to approach in that case. So this is special, and so is this. Okay? The limit of a number is just the number itself. So you notice these two numbers are different. What x is approaching and what the number is, they're not the same. In this case here, the function is x, but whatever the number is approaching is going to equal that number. Okay, so there's a little bit of a difference, and I just wanted to bring that to your attention. Alright, so in the first part of the homework, like 1 through 9, what you're doing is you're using your calculator and your 2 fingers, right? And you're looking at some function, like maybe number 5, and let me just graph it as an example. So number 5, I'm going to put it in parentheses, is cos x minus 1, close the parentheses, divided by x. And this limit is when x is going to 0. So I know if I plug a 0 in, I've got an issue right away, right? So let's graph this, and I'm probably going to have to change my window here. Alright, so let's do a zoom 6. Now I know that screen's getting like kind of weird with the lines and everything because I'm filming the screen. So let me just try and move the Elmo a little bit. Okay, so that's not bad. It's doable. And what I see here is, the limit as x approaches 0 is 0, right? If I come in from the right-hand side, it's 0. If I come in from the left-hand side, it's 0. And again, I might want to do second format and turn my axes off. Oops. And graph it again just to see is there a hole somewhere over there. Oh, look at that. There it is. So there's another case where the axes, the y-axis, in this case, covered up the hole. So there's still a hole in the graph. There's still a discontinuous spot there, right? The edge of the pool. We can't get to that spot, but we can get really, really close. And guess what? The height is the same from either side of that round pool. All right? So even though I can't manipulate this yet because I don't know how to, because I'm a new calculus student, soon you will learn. And I know if I plug the 0 in, I'm going to have 0 over 0. I've got this, problem with division by 0. I can always go to my graph, and whether there's a hole there or not, I can find the height of the function. Another thing I could do again is press trace. Oh, does it work when the X is not off? Trace 0, and hit enter. And you notice when X is 0, Y is not giving you a number, and that's because there's a hole there. All right, so you have to do that kind of a thing visually from the graph going from the left and the right. And also, you would have to state, so maybe on an AP FRQ, you'd have to say, the limit as x approaches 0 from the left of this function is equal to 0, and the limit as x approaches 0 from the right of this function is equal to 0. Sorry. Therefore, the limit as x approaches 0 of this function is equal to 0. So the limit exists, and its value is 0. Capiche? Oh yeah, I just wanted to demonstrate the break one more time in case somebody was not in class. So we went over this problem in class. We've got the graph of f here, and there's a lot going on, right? So again, graphically speaking, if the limit approaches -3 from the left, so that little minus up at the top like an exponent means from the left of this function, we are going to start on the left, and we're going to head toward -3, and we see there's a hole there, but the height is 1, right? And if we approach that same value, -3, from the right side, well, it's still headed toward a +1. So therefore, we can say the limit as x approaches 3 is 1 because it exists. At +2, the limit as x approaches 2 from the left, so we come in from the left-hand side, it's -1. Sorry, hold on. I'm sorry about that, but apparently the whole world is calling me about the oncoming hurricane, and so God forbid if I don't answer the phone, then they'll think it's already here or something. So anyway, sorry. So where were we? As x approaches 2 from the left, the limit's -1. The height is -1, or it's tending toward -1. The limit as x approaches 2 from the right, though, is 1. So you see there's a break in the graph here, and the limits are different. So therefore, when they ask what's the limit as x approaches 2, you would have to say it does not exist. Okay? So that's really important. What else? What else? What else? Is there anything else in here that I could talk about? I guess not for right now. So anyway, that ends 2.7. You've got some homework, which I believe I listed on EDSB. In the event that I didn't, I'm pulling up my photos right now, a picture of my board. And let's see. Yikes. What do I have here? Page 125. No, that's the wrong one. Oh, I didn't take a picture of my board. So I hope I put it on EDSB, but I would say, for sure, you're going to do 1 through 27 odd in this section. All right? And if you have any questions, we'll go over them on Tuesday or whenever we return back to school. Okay? So have a good night. This was the final in the hurricane series. So stay safe, and we'll see you next week.